Okay, so this is the second part of volume by rotations. We're going to find the volume of the solid generated by revolving the region enclosed by these graphs about different lines. So the region enclosed by these graphs, if we were to graph x squared and the cube root of x, the region that's enclosed by the graphs is like the petal of the flower here. So now if we rotate that about the x-axis, that's going to be a dx problem. So the reflection would look like this. So we can just get an idea of what we have. So we definitely have a hole in the middle. But remember, we always get our radius from starting at the center and going to the edge. So the center to the inside and the center to the outside. Okay, so the outside radius this time is determined by the cube root function, and it's the difference between the cube root of x down to the rotation, which is 0. The inside radius is the difference between the x squared down to the axis, which is 0. So our rotated volume is going to be the inside and outside radius. So we're going to still again do this like we have a cylinder with a hole drilled out in the middle. So we're going to do pi r squared h minus the smaller pi r squared h. So it's pi. The height of our shape, since again we're going this way, is going to be the dx. So the height is the x part, from 0 to the intersection. And so now I know from graphing, but also from setting the equations equal, that x squared is going to equal the cube root of x, only at x equals 0 and x equals 1. So then we have the outside radius, which is the cube root of x squared, minus the inside radius, which is x squared, times the height. So remember, you got to be careful about the x squared squared situations. A lot of times the second square is forgotten. Okay, now if we were to take that same shape and revolve around the y-axis, we're going to have a different situation. Because we only have this part of the x squared graph, and we have one part of the x cube root graph that we're going to use. But when those rotate around, if we go around vertically, we have to have a dy. So we're going to have to convert our equations. So as we rotate around, we're still going to have a hole. The height now is determined by the y. So we are going to have a dy equation. We are going to have pi. So the y values also happen to go from 0 to 1. And so we have an outside radius squared minus an inside radius squared. So now if we look at these graphs, if we have y equals x squared, then x is technically plus or minus the square root of y, but we're using the positive x side, so we have to choose the positive square root of y. If y equals the red graph, which is x cubed, then x is only the cube root of y. Nope, sorry, I just wrote that backwards. If y equals the cube root of x, then x is only y cubed. So now working from the center of our shape, toward the outside, from the center of our shape to the outside, we get the inside radius and the outside radius. The inside radius is the difference between the y-axis and the y cubed curve. The outside radius also is the y-axis, but then the square root of y curve. So this is really x equals 0 when we're on the y-axis. So this difference for the inside is y cubed minus 0. And for the outside, it's the square root of y minus 0. So the outside radius squared and the inside radius squared. Okay, now, again, we're taking the same shape, but this time we're going to rotate around. Y equals 1. So we only have this part of the graph for x squared and the right-hand side of the graph for x cubed. Sorry, cube root of x. I keep saying that backwards. Okay, so now if we rotate around the line y equals 1, that's going to go right through the intersection of the graphs. So we're still going to have a flower petal type reflection. We're still going to have a hole in the middle. But this time we're rotating horizontally, so it's a dx. So we go back to having the x squared curve and the cube root of x curve. So now rotating around The radius goes from the axis of rotation to the inside and the axis of rotation to the outside. So the inside radius, remember this line was y equals 1, is 1 minus the cube root graph. The outside radius starts at 1 and goes down to the x squared graph. So we have pi. The x values travel from 0 to 1 to give us our height. Okay, but now we have the inside and outside radius. It's going to be a little more complicated to put in. So we have the outside radius squared minus the inside radius squared dx. And the outside radius is 1 minus x squared. The inside radius is 1 minus the cube root of x. Okay. All right, so this time we're going to do x equals 0, which is the y-axis. Y equals sine and y equals cosine of x just to the first intersection. So the y-axis, or x equals 0, y equals cosine of x, and y equals sine of x just to the first intersection. So we need to know the first intersection happens when x is pi over 4 and cosine and sine are both equal to root 2 over 2. So if we take this shape and rotate it about the x-axis, we're going to have this claw type shape going on. So we do have a hole in the middle. Remember, we start at the rotational center to figure out where the radius is. So we go to the original curve so that we don't have to write new equations for the reflection. So the original curves. So the outside radius is the cosine graph minus 0. The inside radius is the sine graph minus 0. So it's pi from 0 to pi over 4, the outside radius squared minus the inside radius squared dx. Okay, now if we take that same shape and rotate it about the y-axis, we have the cosine graph, which is coming down. We have the sine graph, which is increasing, and we had x equals 0, or the y-axis. So we're taking this shape and rotating it around the y-axis. So what that means, if I do the rotation, is that we're going to get this reflected space, and there's actually no hole. So we really don't have an inside and an outside, but what we do have is the concept from geometry class, where your teacher asks you to find out how much ice cream cone would hold, or how much was the volume of the ice cream. We're going to find the volume of the cone plus the volume of the half sphere, so to speak, even though ours is not quite a half sphere exactly. So what we're going to have to do is do this graph in two pieces. We're going to do the rotation for the bottom half of the graph. So I'll call this part the R bottom, as the distance between the sine graph and x equals 0. And then we're going to do the top part, the R top, as the rotation around that just involves the ice cream part, which is the cosine. The problem is we're spinning vertically, which means we need to do a dy. So we're going to have to convert our functions. So if y equals the sine of x, then arc sine of y is equal to x. If y equals the cosine of x, then arc cosine of y equals x. I'm going to color those backwards, so I'll switch this. So the cosine is going to be the red one now. The blue one will be the sine. Okay, so now for the bottom part, for just the cone part of our shape, our radius is determined by the 0 and the sine graph. So the bottom part is sine inverse of y minus 0. The top part, the ice cream part that domes up, is the cosine graph minus 0. So our radii are going back and forth in this direction that we have here. Okay, so again, our radius goes from the axis to the curve. All right, so now for our volume that we would set up, we would have to do two separate integrals. The integral for the bottom part, for the cone, starts at y equals 0 and stops at the height of the intersection. And we already said that the x value is pi over 4 and the height is root 2 over 2. So from 0 to the y value of root 2 over 2, we have the bottom part, the cone, sine inverse of y squared dy. So it's just pi r squared h. Plus the ice cream part at the top starts at a height of root 2 over 2 and stops at the very top of the graph. Well, the very top of this graph is the top of the cosine graph, so that's 1. So we have pi r, which in this case is cosine inverse of y, squared dy. Okay, so for this next section, I'm going to zoom out a little. Let me set my transparency a little bit here. We have something weird going on. I just want to be able to move my graph up a little to see. So what we have is this space being rotated around to make the fuel tank of the plane. Okay, so it's intersected between y equals the curve and y equals 0. And y equals 0 is just the x-axis. So we reflect that space. But remember, when we do our problem, we always have to use the original curve. So this is the original part. That's the part we have to use. So our rotation for our radius is just going to be the difference between the curve and 0. So the r is really this curve minus 0. So the volume is going to be pi. The intersection starts at x equals 0 because of the x squared being 0. And stops at x equals 3 because of the 3 minus x being 0. And then it's this shape. So the y value squared dx. So if I had to anti-derive this by hand, it wouldn't be a horrible one to do by hand because of the fact that the square is going to cancel the square root. So I would have pi over 100 that I could hold out. And then I would distribute to get 3x to the 4th minus x to the 5th dx. So I have pi over 100, 3x to the 5th over 5 minus 1/6 x to the 6th from 0 to 3. So if this were a free response non-calculator, I would get this as pi over 100. I would leave it as 3/5, 3 to the 5th, minus 1/6, 3 to the 6th, and then minus 0. So I'm going to plug in 0 and just get 0. Okay, now if I were to substitute all of this instead, starting from here into my calculator and never do any of it by hand, this would simplify or reduce to a approximation of 0.763. Now this is the only type of problem that would ever put units. You normally do not make up units for any of these area volume problems, but this one gives us units. So if x and y are measured in meters, we are finding volume. Our volume is going to be in meters cubed. Now, I wanted to revisit a topic that we have done before, but I wanted to talk about the region bounded by curves cut into equal areas. The easiest way to do this is to find the entire area. So from x equals 0 to x equals 9, A has to be in that interval, the region bounded by these two curves, which is really just the square root of x and the x-axis. So if I want to cut that area in half, I'm going to find the total area first. And the total area anti-derives to be x to the 3/2 over 3/2 from 0 to 9, which is 2/3 of 9 to the 3/2 minus 0 to the 3/2. So that's 2/3. The square root of 9, because remember roots grow on the bottom of trees. So the square root of 9 is 3, and 3 cubed is 27. So we get 9 times 2, which is 18. So there has to be some A between 0 and 9 where the area would be halfway across, because we want 2 parts of equal area. So halfway would make this total area 9. We've already done the antiderivative, so we can copy that part down, but instead of 0 to 9, we're going to go from 0 to A. So that means we would have 2/3 A to the 3/2 minus 0 to the 3/2. So then 2/3 A to the 3/2 has to equal 9. That means that A to the 3/2 has to be 27 over 2. That means A has to be 27 over 2 raised to the 2/3 power. Since we're doing the cube root, because roots of trees are on bottom, we don't have to do plus or minus. It's an odd root. So that's our answer. Okay. That's different than finding the volume. So we have the same shaded area, but the volume is the rotation around the x-axis, makes like an acorn. And the radius is the height, root x minus 0. So if we find the total volume would be pi from 0 to 9, the radius squared dx. But that's pi 0 to 9 x dx. So that's pi x squared over 2 from 0 to 9. So the total volume is going to be 81 pi over 2. There has to be a place in between from 0 to A where that same volume, which would antiderive the same way, has to equal half of the total volume. So the volume to A has to be half of the total volume. So that means what's really nice about this is this pi over 2 is going to cancel with this pi over 2. That leaves me with A squared equals 81 over 2. A technically is plus or minus the square root of 81 over 2, but we have to find a value inside this interval. So inside that interval means I can only have A equal to the positive square root of 81 over 2, or positive 9 over the square root of 2, or positive 9 root 2 over 2. On a free response, I would stop there. Now I wanted to do some extra practice on area for E, because we struggle with this sometimes because of the algebra involved with the E. So if I do growth and decay, I have to know what those look like. So that if I'm looking for the area between, just doing area, E and 0, that's really E, so negative x minus 0, from 0 to 1 dx. So e to the negative x antiderives as negative e to the negative x from 0 to 1. So that's negative e to the negative 1 minus e to the 0. So that's negative 1 over e minus 1. So as a free response, I could leave that. As a multiple guess, you'd probably see that as 1 minus 1 over e. For number 9, if I were antideriving between the curve and the x-axis, and it should have also said x equals 0. Sorry about that. Okay, so otherwise we wouldn't have a bounded area, or the first quadrant area. We're going to do the antiderivative of e to the x over 2 plus e to the x dx from 0 to 1. That means that my u has to be 2 plus e to the x. Du is just e to the x dx. So I have du over u. And I have to change out my limits. So if I substitute into here, I get 2 plus e to the 0, which is 2 plus 1, so 3. For the top part, I end up with 2 plus e to the 1. So this answer derives to be natural log absolute value of u from 3 to 2 plus e. So that's the natural log of 2 plus e minus the natural log of 3. I absolutely cannot cancel anything across that plus. What I could do is put these back together as a fraction, because a quotient becomes a difference inside of natural log, so that could work. Okay, for this one, if we substitute 0 into here, we're going to get 1 times 0. The e function is going to grow, and the sine function are going to grow up until we get to pi. And at pi, sine is going to be 0 again. So regardless of what e is, 0 times e is still going to be 0. And then as the sine is negative, the e is going to make it larger. So we're going to have an oscillating function. But we want the first one between y is 0, x is 0. So we have this. So the area, so the antiderivative from 0 to pi, e to the x sine of x dx. And this one you would have to do on your calculator. For the decay function, e to the negative x, going from 0 to 4, the antiderivative of e to the negative x minus 0 between these two curves from 0 to 4 is negative e to the negative x from 0 to 4. That's negative e to the negative 4 minus e to the 0, which is negative 1 over e to the 4 minus 1. So this could be my free response answer, but my multiple guess answer would most likely be 1 minus 1 over e to the 4. Okay, for this next one, regardless of the fact that we have the x in front, this is still an e to a negative power. This is still going to be a decay function. E is much stronger than x, so it's going to force this function to decay down to 0. So we're looking for e and y equals 0. So the area, and then we're bounded by 0 and root 2. So 0 to root 2, x e to the negative, and I'm going to write this as 1/2 x squared because that makes it look less like a quotient, because it really is not a quotient rule, dx. That makes the u equal to negative 1/2 x squared. So du is negative x dx. So negative du is x dx. So if I substitute the x values into the u, 0 still comes out as 0. Root 2, however, gets squared to become 2, but negative 1/2 of 2 is negative 1. And then the inside part is negative e to the u du. So now I can flip this part, because these are in the wrong order, and it'll fix the negative. That makes this positive negative 1 to 0, e to the u du. So that's e to the u from negative 1 to 0. So that's e to the 0 minus e to the negative 1. So 1 minus 1 over e. Okay, this next part, again, we want to talk about what happens with the algebra on these, because that's the mistake that we make. It's not the e derivatives most of the time. Most of us have memorized our basic derivatives so that we know the derivatives and antiderivatives of our functions. At least I hope you have by now. Otherwise, your final exams are going to be awful. Okay, so again, this is a growth function because e is raised to a positive power. So the half slows the growth down a little bit, but not that much. So we're still talking about e being a growth function, and e to the 0 over 2 is still going to be 1. And it wants the volume in the first quadrant with x equals 2. So that means this part rotated about the x-axis. So the x-axis is really y equals 0. So we're going to spin around y equals 0. But it's the x-axis, a horizontal makes dx. So I can think about, again, my reflected curve and the type of shape this is going to make. It's kind of like a Rolo candy. Okay, now, there's no gap or space, so I just have one radius, and that radius is the difference between the e curve and the 0. So there's no inside radius, and we just have e to the x over 2 minus 0 as our outside radius. So writing this down, I get pi, starting at x is 0, ending at x is 2 because that's the height of my shape, e to the x over 2 squared dx. So it's pi r squared h. Now the algebra problem that comes in is from the e to the x squared over 2. So, kind of as a sidebar, think about what happens if you have x squared cubed. You get x to the 6th because power to power means multiply. So this is the same situation. Power to power means multiply, and x over 2 times 2 is just x. Well, that's lovely, because when we do this work by hand, which we would have to do for this type of question that's this simple, we end up with just e to the x on the inside. And the antiderivative of e to the x is e to the x from 0 to 2. So we have pi e squared minus e to the 0. So that's pi e squared minus 1. And that's our answer. Okay, for this next question, we're going to use our calculator. But even without my calculator, sometimes they ask me to set up but do not evaluate. So if I had to set up but do not evaluate, then I need to know what these functions look like. I know that this e function is a decay function because of the negative. So I have some sort of e decay. It's going to be a little taller because if I put 0 in here, I get 6 times 1, so it's going to be up at 6. And then we have the square root function. So I really could make this a little taller. And then my square root function is going to be below. But now it says between x is 1 and x is 4. So I'm not really quite sure where that falls on my graph. So I'm going to take out my calculator. And I'm going to graph. My y1 is going to be 6e. And be careful again substituting this into your calculator. You want to make sure that when you plug this in and type, that you watch out for those zeros and the decimals there. So it's negative 0.2x. And then we have the square root of x. I'm going to zoom 6 just so I can see what my normal window would look like. And I'm going to figure out where that intersection is. So the 1 is not a big deal, but I'm not quite sure where the intersection is between the two graphs as far as where the 4 would fall. Because the intersection is at 4.95. So that means, I'm going to cheat a little. I'm going to put my graph down here. I'm going to cover that one up. So now if I go from 1 to 4, I'm going to hit before the intersection. So that's going to be this part here. So if I were to reflect that, and it says we're going to rotate about the x-axis, that's actually here at y equals 0. If I reflect that across, I have kind of a volcano. And then I do have a space. So I'm going to have an inside and an outside radius. So I always go from my original curve to the center. So the outside radius is the 6 e to the negative 0.2x down to the y equals 0 axis. So the x-axis here. And the inside radius is the square root of x minus the 0. So my volume is pi from x is 1 to x is 4. The outside radius squared minus the inside radius squared dx. Now, I may not at any point in time ever write calculator notation on my paper and get credit. What I could do, however, is make a small calculator notation for myself as long as I mark it out. You don't want the AP reader to grade it. So what you could do is say, well, I'm going to do the integral from 1 to 4. I know my calculator has integral brackets to start with, or parentheses. But I have this stored into y1. So that's going to be y1 squared minus y2 squared. That would allow me to put this into my calculator without having to mess that part up. So I could copy pi, the integral, from 1 to 4. The y1 graph squared minus the y2 graph messed up second. The y2 graph squared. And then I don't have to worry about all this extra set of parentheses that would technically have to go like that into the calculator. So I don't really have to have those written down per se, although it is good form. But now I don't have to worry about having to open and close parentheses inside my calculator. So now I have the first curve squared minus the second curve squared because of the 0. I really didn't have to worry about the other part because of the 0. And after I got my answer, 108.882, I could just do this. I don't even have to mark the whole thing out. I would just mark a line through it because once you do that, no one will grade it on the AP exam. We'll notice it, but we won't grade it at all. We'll just go with what you've written here. Okay. For the last question on this part, it says, let R be the region bounded by this curve. Now, what's going to happen is this side's a growth and this is a decay. But you're adding it together. So basically the idea is, if I were to substitute 0 into here, I would get e to the 0 and e to the 0, which actually is 2. This 1 plus 1. And then this side's going to grow while this side approaches 0. So basically this is e to the x over 2 plus 0. So it's still growing. The left-hand side, the decay function is coming down, and this e function was 0. Well, that's still e plus 0, so really this is just going to be the e part here. So it's almost parabolic. And now we're doing that down to y equals 0. So these two. From negative 2 to 2. So I really have this area. We are then rotating that about the x-axis. So we have a dx question. And the reflection is going to look like this. So what I have is 1 radius because this is where I'm spinning from the center. So I don't have an outside radius, but my inside radius is e to the x over 2 plus e to the negative x over 2 down to 0. So my volume is pi from negative 2 to 2, the r that we just found, squared dx. Now, what we have to be careful about is how we FOIL this, and it does absolutely have to be FOILed. So I would write that off on the side. And remember, when we multiply two things together, we add the exponents. So I don't really want that graded, but I could remind myself that that's how it works. So when I multiply e to the x over 2 times e to the x over 2, I'm going to add my exponents. So half of x plus a half of x is 1x. When I multiply e to the x over 2 and e to the negative x over 2, I'm going to add my exponents. So half of x minus half of x is 0, but I still have the e. So it's e to the 0. Same thing for the inside. It's e, and I add my exponents and get 0. And the last part, I'm going to add my exponents and get negative x. So what I'm actually anti-deriving is pi negative 2 to 2, e to the x plus 2 plus e to the negative x dx. Now, this is where the fun, cool stuff comes into play. Okay, so what we're going to have here, fun, cool stuff, is we have an even function. An even function is perfectly balanced on the left and the right. So what I can do is I can just do one side and double it. So that's going to make this much easier for me to substitute in. So I'm going to do the fact that this is even and double just from 0 to 2. So I'm taking just the right-hand side and doubling it. So I don't have to worry about plugging a negative into a negative exponent and a negative into a positive exponent and figuring out what happens. I'm only going to plug in 2 and 0. So I'm going to hold the 2 pi and anti-derive. The antiderivative of e to the x is e to the x. Antiderivative of 2 is 2x. The antiderivative of e to the negative x is negative e to the negative x. And then from 0 to 2. So if this is a free response question, I still have my 2 pi. I would substitute in parentheses e squared plus 2 times 2, which is 4, minus e to the negative 2, close parentheses. So top minus plugging in the bottom, which is e to the 0 plus 2 times 0 minus e to the 0. So it might not look like it's that much easier, except voila, e to the 0 minus e to the 0 cancels, and that's 0, so this whole term is 0. And that's where the super cool fun stuff happens. So now my free response answer could just be this. If it were a multiple guess, it probably wouldn't look that much differently. It would just be e squared plus 4. Worst case scenario, 1 over e squared. That's it. They probably would not even distribute the 2 pi because it just really wouldn't make it any nicer.